So here's the recurrence relation I've been talking about for a while here, and here's a differential equation of the same class. They have a lot of similarities. For one thing, there are the same names for classifying them. The equations obviously look pretty similar. They also share this so-called characteristic equation, which is used for solving both of them. And another thing that they have that seems to be in common is the generating function of this recurrence relation looks very similar to the Laplace transform of this differential equation. So this is the Laplace transform of this one. If you don't know where this is coming from, just take Laplace transform of both sides, solve for big Y of s, and you'll get this. And the thing that most people usually forget about is the convergence of the Laplace transform. And in this case, s has to be greater than the greater of these two. I'm leaving the name of these things as a surprise to try to make you keep watching my videos, but it's greater than the s must be greater than the greater of the two roots of the characteristic equation. And over here you see that x has to be less than the minimum of the reciprocals of them. And so there's a lot in common with these two equations too. On the top I grouped the constant terms and the linear terms. Over here, linear terms, constant terms. You'll notice that here I have a times f0. Here this is a times the zeroth derivative of y evaluated at 0. Here af1, a times first derivative, bf0, b times zeroth derivative. On the bottom here you have, this is literally just the characteristic equation written in s. And over here, this is very similar to the characteristic equation except that constants are reversed. And so you might notice that or you might think like maybe there's a way we can get from one to the other. And in fact, if you take this one here and you do a variable substitution, you let x be 1 over s, then you'll get this. So one simplification I made is I multiplied top and bottom by s squared once I replaced with this substitution, and then I factored an s out of the numerator. And you get this thing here. And this is identical to this Laplace transform. The only difference is this factor of s. You'll see that this is an f0 here, where this is like y of 0. f1 corresponds to y prime of 0. And so f0, that's y of 0. f1, that's y prime of 0. And then the only other thing is that here the convergence, s has to be greater than the maximum of these two values, where here I have these absolute value signs. And so I'll talk about that more in a second. But you'll notice that this is like hinting that the function f of n is just the nth derivative evaluated at 0 of the function here that satisfies this equation. By the way, I'm assuming here y is a function of t. So this is something that I'm going to explore more in the next video. And so what you can do is you can write a relationship here, f of x, which is just f of 1 over s, since I'm saying x is 1 over s. This ends up just being s times y of s. And if you remember your Laplace table or whatever, you might remember that s, if you have s times the Laplace transform, that's like, well, it's almost the Laplace transform of the derivative of y. If you had s times y of s minus the initial value y0, little y of 0, then that would be Laplace transform of the derivative. And so what you can do is you can just say subtract it, add it back on, and then you get this equation here, which relates the generating function of this recurrence relation to the Laplace transform of this. And so it's just kind of cool that that the two are related. So theoretically that means that if you wanted to solve this, you could take the generating series. It would be a lot of work and I don't recommend it. then you could like convert this to a Laplace transform, I don't know, go backwards and solve a differential equation or something. But it is just like a link between these two equations, which is pretty interesting. The more interesting one is this one here, which I'll talk about in the next video again. This is a much simpler link between the differential equation and the recurrence relation than this one is here. So the idea is the generating series, this is pretty much the same thing as the Laplace transform. And so what I want to talk about now is just like how can you extend the idea of using a generating function to solving other types of functional equations. A recurrence relation is a functional equation that has a discrete variable. But functional equations, more broadly, could be any kind of recursively defined function. And a differential equation is one particular type of one. So the other technique that I've shown for solving recurrence relations, which was guessing and then using induction, that can't really be extended. The guessing can be used to solve functional equations in a sense, but you can't use induction to confirm your answer with if you don't have a discrete variable. And so this is pretty cool because in this case you actually can take the idea of a generating function and extend it to other functional equations. And so now I'm going to talk about that. So the idea with a generating function is you have this power series. I'm calling f of n, that's the input function. And then this x to the n, I'm going to refer to that as the kernel. And so depending on what you put in, you can't really look at the convergence of this thing without knowing what f of n is. But you can look at a couple examples here. If you put in if your input function is just a constant function, then you've got a geometric series. It converges when absolute value of x is less than 1. This is what it converges to. And generally speaking, the convergence for these things is going to be absolute value of x is less than 1. Certain influential functions, such as exponential functions, which increase at a very high rate, or they decrease if it's a decaying exponential, they decrease at a really rapid rate, these will actually affect the convergence. And so if you put in an exponential function lambda to the n, you find that the convergence is then adjusted. So notice that if lambda is greater than 1 in magnitude, in other words you have an exponential growth function, the convergence is shrunk. And if lambda is less than 1 in magnitude, then your convergence gets bigger. And this is what it converges to. And then you could also have factorials. Those increase even faster. And the 1 over n factorial, if that's your input function, that actually provides enough dampening against this kernel function that even for values of x larger than 1, where this kernel part is going to get extremely large, this 1 over n factorial provides enough dampening to force this thing to converge in any bounded interval. It will converge pointwise to e to the x. And then of course if your input function was n factorial, like in the numerator, that would force this thing to diverge everywhere except x equals 0. But the point is, generally speaking, we can talk about when this thing is likely to converge, and that's going to be when absolute value of x is less than 1. And of course, depending on what you put in, that might not actually be the case. But the idea here is, how can we take this idea and extend it to make it able to handle continuous functions? Because right now you have a discrete sum. Your input is this function of n, discrete variable, and each term represents each term of this sequence, or this function, f of n. So how can we extend this idea to continuous functions? Well, the continuous analog would be an integral. And so here I'm just going to replace this f of n, the input function. I'm now just going to call that f of t. I'm replacing the discrete variable n with a continuous variable t. And this dt is really just because you're dealing with an integral. It's nothing changing there. So this is exactly the same thing. We can look at when this thing is likely to converge, and there is one slight difference here. This one was likely to converge when x is between -1 and 1. But notice when x is between -1 and 0, you have alternating series here. If x is negative, then you put a negative number to an even power, it's going to be positive. Put a negative number to an odd power, it's going to be negative. So you can't really do that type of thing when you're dealing with a continuous variable, because what if t is like an irrational number or something? It just gets really ugly. So you have to limit this convergence not from -1 to 1, but just 0 to 1. And so then I'm just going to make this change here. Actually, this isn't a change at all. I'm just introducing a new variable s. And the reason I'm doing this is just because it's going to make it look nice. If I choose this substitution, then my convergence interval changes to s greater than 0. So and the integral then changes to this. You can see that generally speaking, this thing will converge if you multiply, if your kernel is a decaying exponential function, if s is greater than 0. That's the only reason for the negative sign, is just so that this isn't s is less than 0. But the point is, this thing is called the Laplace transform, and all it is the continuous analogy of the generating function. And so if you think back to a second ago, I mentioned there's a slight difference here. This function here had the generating function converges when s is greater than the maximum of the absolute value of these two things. Over here there is no absolute value signs. Well, that's just because that's just because of the alternating series thing. You can't have when you're dealing with the Laplace transform, you can't have there's no such thing as like an alternating integral. There's only alternating series, just because of that problem. Like, what if you had like -1 to the pi or something? So that's the only reason that little thing comes up.